Awesome! Welcome to the video about counting and enumeration. So, here are the key terms. When looking at situations involving counting, it is also often not practical to count things individually. First, however, we must look at the fundamental principle of counting, which is sometimes referred to as the multiplication rule, which states if there are m ways of doing one thing and n ways of doing another thing, then there are m times n ways of doing the first thing, followed by the second thing. So there are m options of doing the first thing, let's say 10. 10 options of doing one thing, and let's say 5 options of doing another thing. There's 5, you could have each of the 10 first things times paired with each of the 5 second things. So 10 times 5 would be 50. Permutation is an arrangement where the order of members in a selection results in unique groups. So we're going to count something as different if we start with a particular person and end with a different person. So, for example, lining people up is a permutation because if I'm first and Jill is second and Harry is third, that's a different line order than if Harry goes first and Jill is second and I'm third. Or Jill is first and Harry's second and I'm third. All of those are different line orders and unique groups. Whereas a combination is an arrangement where the selection of the same members results in the same group regardless of the order of selection. So a combination is where you're making groups of items. So a combination would be a group of me and Jill and Harry. And it doesn't matter if I was selected first or if Harry was selected first. As long as the same 3 people are in the group, that's a combination. So let's take a look at how this plays out in a couple examples. First example, there are 3 t-shirts and 2 pairs of jeans in the cupboard. Why would you put clothes in a cupboard? Don't know. How many possible outfits are there? So we know for an outfit we're going to need 1 t-shirt and 1 pair of jeans. So we're selecting 1 t-shirt and 1 pair of jeans. Now we're assuming these all look cute together. So we have 3 options for the t-shirts, and each of those 3 options can be paired with either the first pair of jeans or the second pair of jeans. So that would be 3 times 2. That's the multiplication rule. 3 times 2 is 6. There are 6 different outfits that you can wear. Each of your 3 t-shirts can be with the first pair of jeans, and each of your 3 t-shirts can be with the second pair of jeans. So 6 outfits. Similarly, an ice cream shop offers 3 types of cones. You've got the waffle cone, you got the sugar cone, you got the, is there another one? Chocolate dipped waffle cone. And 5 different flavors of ice cream. So you've got your mint, you've got your vanilla, you've got your strawberry, your rocky road, and your toffee nut. How many possible ice cream cone combinations are there? Well, all 3 of those cones could be ordered with the mint, but all 3 of those cones could also be ordered with the chocolate or the vanilla or the strawberry. And so it would be 3 times 5. You're picking 1 out of those 3 cones and you're picking 1 flavor of ice cream. So we're assuming it's just a single scoop situation, 1 type of cone, 1 type of ice cream. So that would be 3 times 5 because you get to pick 15 different order combinations. So as you can see, here are our solutions. For each t-shirt, there are 2 possibilities of jeans. Altogether, we have 3 lots of these 2 possibilities. So 3 times 2 is 6. For each of the 3 cones, there are 5 possible toppings for your ice cream. So 3 times 5 is 15. Now we can also display this with a tree diagram, or some people like to use a box diagram. So this would be the t-shirt example with a tree diagram. Each of those 3 t-shirts, you can choose any of those 3. And once you choose a t-shirt, you have 2 options for pants. So once you choose a t-shirt, 2 options for pants. If you run down the branches of each of these parts of the tree, that's one option would be t-shirt number 1, pants number 1, then t-shirt number 1, pants number 2, second option. There are 6 total options in your tree diagram. You could also do this with the box method. So the t-shirts are, my 3 t-shirt options are this way, and my 2 pants options are across the top, the column headings. And then each cell represents a different outfit. So I could wear t-shirt 1 and pants 1, or t-shirt 1 and pants 2, and you can see clearly there are 6 different outfits represented here. Now, these box diagrams are cool when you only have 2 different things that you're choosing. But if we were going to pick a t-shirt and pants and a jacket and some socks, the third one would make it a cube or a rectangular prism. And then the 4th dimension gets a little tricky to draw. So I would probably resort to a tree diagram if I was going to add additional branches off of this. It's very easy to continue to add branches to a tree diagram. That would be my recommendation there. The local pizzeria offers a choice of 2 pizzas, supreme or vegetarian, 3 sides, chips, salads, or coleslaw, and 4 different drinks. For dinner, I have to decide 1 pizza, 1 side, and 1 drink. How many possible meals do I have to choose from? We can see that this is the multiplication property because we are pulling 1 thing from each of the different groups. So we have 2 pizzas to choose from, we have 3 sides to choose from, and we have 4 drinks to choose from. So that would be 2 times 3 times 4, which is 6 times 4, which is 24 different meals. How many different car number license plates can be made if each is to display 3 letters followed by 3 numbers? Well, we have 26 letters in our alphabet, and we have 10 numbers, 0 counts, and then 1 through 9. So that's 10 different numbers. So for the first letter, I have 26 options. And did you know in license plates you can repeat letters? So I have 26 options for the first one. Then for my second letter I get to pick, I still have 26 options. 26 times 26 times another 26 for my 3 letters, followed by 3 numbers would be 10 times 10 times 10. So you can see that our first answer is 24. Our second answer is 26 times 26 times 26 times 10 times 10 times 10, because we can reuse those digits, we can reuse those letters. Once they're chosen, they can be used again. So that would be a really ginormous number, 17,576,000 different car number plates. Last one, your friend wants to perform a magic trick and asks you to draw 2 cards, there should be a D in there, from a standard deck of 52 cards. The first card you draw must be placed face down and the second placed face up on the table. How many ways are there of drawing the 2 cards? So for the first card that you draw, there's 52 there's 52 cards in the deck. You're going to pick one of them. So you have 52 options for the first card, and that's placed face down. Now that one card that you picked is out of the deck. It's sitting on the table. The second card, there's only 51 options now. You have 52 options for your first card, but you only have 51 left over because one of them is sitting on the table. You have 51 options for the second card. Therefore, 52 times 51 is 2,652. That's it, 52 times 51. A teacher wants to randomly choose 5 people from the class of 30 to help out at the open day barbecue. And how many ways can this be done? So this is a group of people that are going to help out at the barbecue. Doesn't matter if Bob is picked before Linda, who is picked before Troy. No, if those 3 people are picked, they're still the same 3 people. So we don't want to count unique groups just because we picked Bob and Linda and Troy in different orders. So how we're going to do that is we've got 5 people from the class. So that would be, I would probably draw it like 5 dashes across. 1, 2, 3, 4, 5. So we've got 5 people we're going to choose from the class of 30. Our first option we have is 30. Our next option, 29. Once we pick that kid, we've got 28. Once we pick that kid, we've got 27. Once we pick that kid, we've got 26. But right now, we are counting all of these as unique groups. So if I pick Billy, then Linda, then Troy, that's different than Troy, then Linda, then Billy. What I have to think about is how many of my groups in this situation are actually the same amount of people. The same group of 5 people, just in different orders. How many ways can I order 5 people? Well, that's 5 factorial. It's 5 times 4 times 3 times 2 times 1. So I'm going to take this answer that I get by multiplying all of these 5 numbers together. I'm going to take my answer and I'm going to divide by 5 factorial. 5 factorial because there are 5 blanks here. And there are 5 factorial different ways to line up the same 5 people. But I'm just choosing them for the barbecue, so it doesn't matter who gets chosen first. I just want the same 5 people. So I'm going to take that answer and I'm going to divide by 5 factorial. Now the second one, a teacher wants to award prizes for first, second, and third place. In a class of 30, how many ways can the prizes be awarded? Assume no students can tie. In this situation, we can see that Let's see. Here we go. So in this situation, we can see that the order does in fact matter. So we have 30 students that could be in first place. Then we have 29 students that could be in second place, 28 students that could be in third place, 27 students that could be in fourth, and 26 in fifth. The order does matter here. Getting first is totally different than getting fourth. So the same 5 students who place and get the prizes, it's different whether you place first or second or fourth or fifth. Therefore, it's called a permutation. So 30 kids, we're going to choose 5 of them. The order matters. So the order creates unique groups. So 30 times 29 times 28 times 27 times 26 is 17,100,720. You can see in the combination, we knew it was a combination because ordering the people in the group differently results in the same group. So that's a combination. And when we do the combination, we have to divide by this 5 factorial at the bottom. We have to take out all of those groups that are actually just the same people rearranged differently. It's like the same people just lined up differently. So that's a smaller amount. The combination is smaller. We have 142,506 if we're just pulling a group of 5 people versus assigning those 5 people to where the order matters, to 2 prizes to slot, the first, second, and third. In an 18-team league, how many ways can the 8 teams for the finals be decided? And in how many ways can the first 4 positions be decided? So we've got 18 for the first one, times 17, times 16, times 15, times 14. Once we choose one, we have one less, all the way down to 11. And in this case, we're looking for just the final 8 teams. So the teams in the final, it doesn't matter where you sit in the finals. If you make it to the finals, you're good to go. You get to compete for the championship. So we have to divide out all of those different situations where the same 8 teams made it. They just sat in different parts of the bracket. It's still the same people in the finals. So we have to divide by that 8 factorial. That results in 43,758 ways to organize those 8 teams for the finals. 8 teams out of the 18 are going to make it to the finals. And then at the end, the first 4 positions, we're assuming that positions means like first place or like top, gold medal, silver is second, bronze is third. I don't know what you get for the last one, like foil or something for the 4th place. I don't know what medal that is. Anyways, so that one, the order does matter. It's totally different to win gold versus silver. So we don't have to divide out anything. We don't want to take away any of our groups. We're just going to do this 18 times 17 times 16 times 15. That results in 73,440 ways for that league. The child wants to draw a picture using only 3 different colors from a set containing 12 different colored pencils. So out of that group of 12, we're going to select 3 of them, and the order doesn't matter. Choosing red, blue, green is the same 3 colors as choosing green, blue, red. So that's called a combination. When organizing those 3 different colors in a different order is the same group, same colors chosen. That's going to be a combination. We're going to have to divide out all those groups that have the same colors, just in different orders. So we have 12 to start from. Once we pick 1, we have 11 left to choose from. Then once we pick those 2, we have 10 left to choose from. So 12 times 11 times 10 would be the permutation way. But because we don't care what order the child picks the colors, it's just picking colors in a group, we're going to divide by 3 factorial because there are 3 factorial number of ways to order 3 colored pencils in different orders. So 220 ways. In the front of a building, there are 3 doors, each to be painted a different color from the 12 different available colors. How many color arrangements for the door are there? In this case, it's different to paint the first door red and the second door green and the third door blue instead of painting the first door blue, red, and then green. Those are different. We're painting different doors, different things. We're not just holding a group of colored pencils in our hands. We're painting doors. So the order does matter here. Each different order is going to create a unique group. Therefore, we're just going to do 12 times 11 times 10. We're not going to divide by anything because we want to keep separate all of those groups where the different doors were painted different colors. So here's the big idea. This is the formal definition. These are the official formulas. I am much more particular that you can get the right answer through reasoning and through drawing blanks and filling in those numbers than I am about you being able to do these formulas. But they do connect in a really beautiful way and the patterns are consistent. And so we have generalized them as mathematicians into formal definitions and formulas. So a permutation is the number of ways of choosing k things out of the possible n, where the order that they are chosen matters, and it's notated NPK. That would be n permutation k. There's actually a button in your calculator that